Hi everyone. Welcome to the class. I hope the exam went well. What is going to happen in the class for the last 3 lectures is that we are going to look at some advanced topics in, let's say, graph representation learning, and we are going to do a series of guest lectures. And I'm going to talk about today's guest lecture next. So the lecture today will be about geometric graph learning or geometric deep learning. And kind of the core concept of today's lecture will be being able to develop models that are invariant to symmetry. So kind of that account for symmetries in the data and are, because of this, able to learn better with less data, more efficiently, and so on. The applications that we are going to talk today about is chemistry. Is basically how do we capture structure of molecules using machine learning. And the lecture will be given by Ming-Kai Xu. He's a PhD student here in the computer science department at Stanford, and actually one of the leaders in this area of using geometric deep learning, diffusion models, things like that for molecular applications. So I'll hand it off to Ming-Kai now.
Thank you, Jure, thanks to Jure for having me today here to introduce both this promising direction in the advanced graph representation learning, and also I can incorporate our most recent progress about graph generation or geometry generation using diffusion models. Okay, I think Jure has nicely introduced me. So I'm a PhD student at Stanford at computer science, working mainly on intersection of generative model and graph representation learning. So the application will mainly about graph generative models on molecular structure, on drug discovery, on protein design, something like this. Okay, so this will be the outline of today's lecture. So first I will introduce what is, when we talk about a geometric graph, what we are talking about, what it is, and what is the key difficulty of developing machine learning models for geometric graphs, significantly different to your previous content for typical graph learning. And the second part is, okay, now we know what is geometric graph. We know what is the difficulty of learning on geometric graph. Then how we develop an effective model for a geometric graph. So we introduced some mainly 2 classes of graph neural network for geometric graph. And the last part is, considering we have already defined the data, we have already developed some modern architecture like a graph neural network, how to use this graph neural network to tackle real-world challenges. And I will introduce our most recent progress of geometric diffusion model, which is capable to generate a very, very realistic molecular structure. Okay, so first part will be geometric graph, and maybe we can have a very brief recap of very typical graph. So what is graph? I think you have learned it for the whole quarter. It's adjacency matrix and also a collection of nodes. The node have node feature, and they are defined by some connection of the adjacency matrix. And occasionally, in the adjacency matrix, the AIG also can contain some edge feature, so we want to learn over such graph. Yeah, very typical thing. And I think, these 2 equations, you also have learned it for many times. So how to do learning on graph structure, we actually use the graph neural network, and it is mainly composed of 2 steps. So one step is aggregation, currently we are on one node and we have multiple neighbors. The neighbor will generate or predict, or we want to learn some message from the from the neighborhood, and the neighborhood will pass their message toward you. You will learn aggregation function to aggregate the information, and after you aggregated the information, you will also have an update function to learn how to update current node embedding. So multiple perspective of understanding the traditional graph neural network. So these are two most I think well-known or accepted perspective to understand the graph neural network. One direction is just look at one layer and you see, oh, it is one node and there is neighbor. You repeatedly pass the message and aggregate the message and update node embedding. And I think the computational tree has also been incorporated in the lecture. So when we're considering multiple graph neural network, you can see in current layer, you aggregate the information from your neighbor. And if you look at the before layer, you can see your neighborhood's embedding. They actually aggregate the information of their neighborhood. So by stacking multiple graph neural network, actually you just exponentially expand your perceptual field and learn more and more feature from the neighborhood, something like this. Okay, and before I introduce what is graph, what is geometric graph, I need to also make a brief recap of the graph level prediction task. I know for graph representation learning, I think we usually concentrate on three kind of tasks. One kind is node level prediction. We want to predict some feature of a node. And another similar application may be edge prediction. So predict some feature on the edge. And but today maybe we first consider the problem on graph level prediction. So this is very useful especially for like a molecular graph, for small graphs. So like we have a molecular graph and we want to predict some feature or property of this molecule. So what we do in addition to the typical message passing neural network, we call it permutation equivariance neural network, but never mind, just a typical graph neural network. Between different layer of graph neural network, we also have some advanced layer like pooling. And I think I also see the previous syllabus. I think differentiable pooling has been also introduced before. So in addition to like just learn the embedding on node level, we also can use some pooling to pool multiple nodes together as a supernode. So this kind of formulation can significantly reduce the number of nodes during message passing, and also it can help to enable some message passing between multiple group of nodes. Or in other words, it makes more sense for molecules, because in molecules there are like chemical rings or something like this. They are very predefined local structure. So this kind of pooling can learn to pool the local structure towards as represented as some pseudo single node. So enabling some message passing between the local graphs makes the information transformation or message passing more effective, significantly improve many tasks for molecular property prediction. Okay, so by last slide, I just introduce like mention how to learn graph neural network for molecules. Now maybe we can have a look again of when we do graph representation learning for molecule, actually what we have as the input. So this figure is pretty typical, right? So it is, again, so node, different nodes are labeled with like item type, and they are connected by valence bond, and the edge can also be labeled with some chemical type, so something like this. But most importantly, actually, we also, in many times, have the 3D structure of molecules. And in many real-world applications, we are very interested in this kind of 3D structure of molecules. For example, when we want to model the how a molecule is act in some solvent or in our human body, how a protein, if you have some disease, there is some protein, there is some functional problem of your protein, and you eat a drug, how the drug will solve your problem. Actually, they are all effective in the 3D space. We want to model them in the 3D space. So it is very informative. And another thing is considering for one molecule. Actually, even one molecule will have different 3D structure in different temperature, in different solvent, something like this. And when they are in different conditions, they will have different 3D, and then they have different property. So it never makes sense to, for some property, never makes sense to input just the adjacency matrix graph and make some property prediction, because the property actually is directly related with the 3D structure instead of the 2D structure. So, okay, so now this is the theme of this lecture, how we do representation learning on these 3D structures. And molecule is the most exciting and promising area of this direction, so geometric graph. I mean, it seems like there will be some killer application of geometric graph neural network. But more broadly, there are also many other scenarios. They are also interested in geometric graph. So in addition to small molecules, there are also a little bit larger molecule like protein, DNA. And these three are organic structure. So for inorganic structure, there are also exciting research on crystal and catalyst. And also, those are in macro world. But in our physical macro world, there are also applications like transportation, the city layout, and vehicle and robotics. So this is really an exciting area. Okay, so now we can formally define what is geometric graph. From your last feedback, I feel like all of you are very familiar with what is graph. So now I can just say, in addition to typical graph, so what's new is just every node is additionally embedded in our Euclidean space. So every node is associated with some 3D coordinates. So more formally, so for this lecture, I will name the traditional node feature like item type as a scalar feature. But for the coordinates, I will name it as tensor feature. I think this is some terminology used in like a physics course. So scalar means that they don't have direction. They are just some number or some value. But for tensor, they are in addition to the like in physics, we usually make notation of tensor as arrow. So in addition to the length of the arrow, we also have the direction. So this is the intrinsic difference. It is directional. Okay. So before I introduce what we are concerned about, like invariant and equivariant, maybe I can provide some very intuitive understanding of why we want to do invariant prediction or equivariant prediction. Okay, so for geometric graph, let me just take a molecular structure as an example. So firstly, maybe let me just introduce the supervised learning task. This slide just show a supervised task of prediction of some property of this structure. Either some functional property of this protein or binding affinity of this protein. So a brief introduction of binding affinity. So when we have some disease, I think the majority of our disease is kind of because there is some protein. There is either some functional protein was disabled or there is some like virus protein in our body. So when we eat a drug, actually, we hope the drug to be like in this figure. Maybe this is our drug. So when we eat a drug, the drug will combine or bind on the protein structure. If the protein is good, maybe we want to like reactivate the function. Or if it is virus protein, maybe our hope is to deactivate it. But anyway, so I just want to see when we eat a drug, the true effectiveness is we hope they can bind together. Okay? But anyway, they are all like a graph level prediction. When we have a 3D structure, we want to have some prediction of the property of this 3D structure. And one interesting thing here is how we represent the 3D structure. So it is the n by 3. So when we have n node, it is n by 3 matrix to represent the coordinates. So every node will have coordinate. So n node have n by 3 matrix to represent the coordinates. But when we do some rotation or translation of this structure, this n by 3 tensor definitely will change. So, but no matter how it changes or how it rotates or how it translates, it is still the identical structure. And we really hope that the prediction should be the same. So this is the high-level idea of what we are concerned about to develop our neural network. So it should capture such symmetry of this physical world. Okay, so this one is for single number prediction. For example, some property. So we just predict a value. Here we also have some other application, like this one. Like in computer vision, we usually call this kind of application as dense application. I mean, for example, if we do image classification, we just want to output which class it is. By analogy, when we want to do like a segmentation of this image, we will output a very dense output of all the pixels to show the segment. So this is kind of similar. I call it a dense output or dense prediction. So for molecular simulation, I think it should be covered in like high school physics, so or university physics. So something like when we can start from a very unstable structure, and molecular simulation means we really want to know what is the stable structure of this molecule. And what we do is we have some method to calculate the electric force between different atoms. And when we have this kind of force, the force can tell us how to move these kind of molecules. And we move again, calculate the force, move the structure, calculate the force, update this structure. And finally, we hope that we can have a very stable structure, which means when we calculate the force again, we hopefully the force is 0 now, finally. So, which means we get a stable structure. And here, so very traditional simulator. So it need actually I think they solve something like a Schrodinger equation and calculate the force. So really expensive. And here what we want to do is like a Schrodinger equation to collect many structure and their corresponding force, structure and corresponding force, and we want to use neural network to learn what's the force on current structure. So it is a dense prediction. I mean, the output is also n by 3. So if we have n nodes, we have n by 3 dimension of forces acting on every node, every atom, and move this atom. So here is another interesting symmetry, right? So considering we do this kind of simulation, we can also rotate and translate the input molecular structure. And how should the force move? So it should rotate together, right? So when we rotate an input structure, the force is mainly by like interactions. So the output should rotate together. And considering translation, no matter how we translate, force will stay the same. So this is another symmetry of this kind of task. Okay, and finally is a very brief idea of what we can do in most modern machine learning, especially in the era of AIGC, you know. So every day we can see Stable Diffusion generate some fancy images, and also ChatGPT generate some fancy stories. So there is also this kind of very exciting progress in graphs. So every day we see many pharma company, drug company, they actually seems like want to solve this drug development problem. They want you give like your COVID virus protein, and they can generate some molecule, probably can bind it on the protein, and they can also another promising direction is like they also have some humans antibody on this virus protein, and they can modify the antibody to make it more effective and develop a method to synthesize that antibody. But anyway, just built on the geometric deep learning, develop a new generative model for these geometries. Okay, so here I want to formally chat about the obstacle or difficulty of this area. So formally we can see when we have a structure. Okay, this structure is here, but we don't know how to construct our coordinate system. We have multiple different ways to construct our coordinate system, and then the coordinates of current geometry will be different. But you know, the atom or the not the atom, the objective or the molecule, no matter in which coordinate system, it should be the same one. Or in other words, if we fix the coordinate system, it can be seen as like we have a molecule structure, and we do multiple like rotation and translation to move it all around in our world. But it is still the same. It should have the same property, something like this. And however, consider how we use traditional graph neural network to process our node feature. A naive way to process the, as I introduced before, for the geometric graph, the only additional feature is the n/3 coordinates. So how to process this information coordinates? A very naive way is just, it is node feature, right? Every node has coordinates. Just concatenate it to node embedding and make it as together as a node embedding and do message passing. The problem seems like it is solved. Is it really solved? Definitely not, right? So we can translate and rotate, and when we translate and rotate, the coordinate will change. And when the coordinate change, after we input into like a traditional graph neural network, every node embedding will change, and the output will change, the prediction will change. This is definitely not what we want. So yeah, this is the problem. Traditional GNN, when they see different like location or orientation of identical geometry, they don't know they are the same. They say, oh, they are different. Okay, so what we want to do is let's try to think about some novel method to make our graph neural network can see, oh, these two geometry, I know they are described differently, but they should be the same. And when we make prediction, the prediction should be the same. Okay, and the before slide is mainly about the input space. So when input space change the symmetry, rotated or translated, we want to make the prediction still the same. But for the output space, there is also some symmetry, which I have mentioned before. Like when we do optimization or simulation of the molecular structure, when we rotate the input, we want to make the predicted force also rotated together. But when we do translation, we hope, the predicted force should stay the same. So there is also symmetry consideration of the output space. So which means, which we use the word equivariant. So input change, output change together. So yeah, this is formally named as equivariance. Okay, so this is the formal definition of equivariance. So firstly, we can abstract our graph neural network as a function. So the function f, we have the input space x and the output space y. So in the example here, so our input space is the molecular structure and the output space is the force. Or more formally, here we are mainly interested in the 3D structure. So maybe you can abstract the problem as input coordinates and output the force. So equivariant means when we have this kind of function, we can apply some transformation of the input space. We name it like rho x. And we similarly want to make some transformation in the output space. We name it rho y. So equivariance formally means for every action in the x space, there is a corresponding action in the y space. They are bijective. So a very natural choice is they should be rotated together and translated. They are not translated together. Okay, just think about rotation first. The rotation is input how rotate. Output should rotate in exactly the same way. So this is the formal introduction of equivariance. Yeah, but yes. So translation is not the case, but still called equivariance. We will present it later. So here is some very intuitive way to have a sense of what is equivariance. So maybe look at this first. We have such a structure and we make false prediction. Okay, we have all the directions. And if we do a row, so it is some transformation, or in practice it is rotation of this system, and then the forces should rotate in the same way. And here is even more informative way to illustrate the equivariance. When we rotate the structure, the two arrows rotate together, which indicates the force rotate together. Okay, so beyond the equivariance, here we also define what is invariance. Invariance is kind of similar. So we have a function, similar function. Here, input an image and we input, who is this famous guy? Okay, so here, this one, okay, yeah, it's Professor Leskovec, right? And then there is some rotation and translation, but you can still know this is still Professor Leskovec. This is not Minkai, right? And yeah, this is the formal definition of invariance. So still the space X, maybe it is an image, and we do some transformation of the image and then input to the function f, which is some neural network. And we hope that no matter how we apply the rho x, we stay the same prediction. This is invariance. And this is a lecture, so I need to present everything in a rigorous way. So formally, invariance is a special case of equivariance. So look like invariant and equivariant. Actually, invariant is just a special case of the equivariance, which means rho y is defined as like never apply any action. So here means no matter how you rotate or translate your input, the upper space transformation is no transformation. Sorry?
This is the bijectivity, though, that you defined before. You said that equivariant functions have to have a bijective relation between px and py.
Yes. Indeed, I realize I may make some wrong statement of bijective. Yeah. Sorry. But yeah, thank you. You are listening very carefully. Yeah. So the rule here is defined as no transformation. So formally, invariance is a special case of equivariance. But in this lecture, I will just, I don't want to lose the meaning of these two words. So when I mention equivariance, I just always want to see, oh, they change together. And when I mention invariance later, I just want to see there will be no change of output space. Okay. But formally or theoretically, invariance is a special case of equivariance. Okay. Here I just have a brief introduction of all the tasks we will concentrate on later for all the neural network design. So what we talk about today is a special, mathematically, it's a special group in our world. So it is called a special Euclidean group 3, SE3 group. SE3 group means we consider the transformation as a combination of rotation and translation. So a little bit more. So there are also just a typical Euclidean space, E3 space. So in E3 space, the additional action is reflection. So but in molecule, when you reflect a molecule, actually the property will change. So we never consider reflection. We only consider rotation and translation. But anyway, I just want to have an introduction of what transformations we will consider today. And the two main tasks are also actually introduced. So a very classic problem is do energy prediction. So every structure we have a potential energy, so how many potential energy it has. So no matter how you rotate or translate, it should have the same energy. So it is a very typical invariant prediction task. And another task is we want to do a force prediction, and as introduced before, it should be an equivariant prediction task. By the equivariant, actually it means equivariant to rotation, but invariant to translation. Yeah, we want to do this kind of prediction. There is some analogy in image domain. What is invariant and equivariant? So when we do classification, no matter how you change, stay the same. But when we do segmentation, what we output is on every pixel coordinates or every pixel position. So they will also change together, considering rotation and translation. So this is equivariance in the computer vision domain. Okay, a summary of all the data and the symmetry we need to consider. And here is a lot of content, but maybe I can concentrate on a graph to make some analogy on the graph. So graph actually is a permutation symmetry group. So by permutation symmetry, we can also consider two types of prediction, a scalar prediction and a dense prediction. Okay, scalar prediction means we want to do graph level prediction. Then, so we predefine order of this graph, and in PyTorch or TensorFlow, it is stored as a matrix. So different nodes, they are combined together as a matrix. But actually, we can change the order of different nodes. They are arbitrarily stored. And when we do a graph level prediction, no matter what order is the different node, we should do the same prediction. So it means the graph never change with different order of the nodes. So this is permutation invariant when we do graph level prediction. we are also sometimes interested in like prediction for every node. So node level prediction. For node level prediction, when we change the order of the input of different node, the output should change accordingly. So this is called permutation equivariant. So they should change in the same way. So I think this is also the design philosophy of a graph neural network to some perspective. The message passing, when you do message passing, you never consider the order of your neighborhood. So the message passing naturally is permutation invariant. And I think this is also one of the reason of the success of graph neural network. Okay, so now let me introduce the how to do graph neural network for this kind of symmetry or symmetric data. A naive way is, okay, although our typical graph neural network couldn't capture the symmetry, we can do some data augmentation, right? This is also, I think, used a lot in computer vision when they do like classification. They randomly rotate and translate the image and force the model to learn the same prediction. Here we can do the same thing. With a single data, we can just enumerate all the positions and force the model to make the same prediction. But this is very expensive, very time-consuming, and also not very natural and elegant. And here, what we want to do is we should develop a GNN aware of symmetry. Just one data is enough. Here is some intuition. So when you never design the geometric graph neural network, you allow yourself to explore in the whole learnable function space. And finally, your data constrain your model to be some subspace, but still very large. But here, what we want to do is you need to constrain your neural network to make it to be just invariant functions. And you significantly constrain the function space you explore. And hopefully, you can effectively learn what you want. Okay, so today I will introduce two kind of graph neural network. One type is invariant graph neural network, and another type is equivariant graph neural. Oh, sorry.
Can you go back to the previous slide? Here, just clarifying, are you using the phrase geometric function to mean the same thing as equivariant function?
Geometric function, equivariant function, not the same. So geometric graph neural network has many different classes. So we will introduce later. So many different graph neural network. And our ideal goal is to develop very